Welcome to my mini lecture Tomography 105. Today we connect abstract mathematics with practical X-ray data. Mathematicians usually think that the starting point of tomography is a set of line integrals of an unknown function. Every pixel value in the radon transform or sinogram is a value of a line integral along one X-ray. But in practice, we measure intensities of X-ray beams and not line integrals. There are a couple of steps in transforming X-ray data into mathematical integrals. The thing connecting those two is the physical law of Beer and Lambert. Here you see a simple example with one block of homogeneous material. We send an X-ray through the block. The graph above shows the change in X-ray intensity as it travels. Let's look at this process more closely, pausing it at crucial moments. The initial intensity of the beam is denoted by I0. It can be thought of as the number of photons per unit time traveling along the ray. When the beam travels through empty space, its intensity remains the same. Inside the block, there are interactions between X-ray photons and electrons in the material. Absorption and scattering remove photons along the way. Therefore, the ray is getting weaker, or in other words, attenuated. Once the beam exits the block, the intensity again stays constant, denoted by I1. The final intensity I1 is always smaller than I0, since the ray can only weaken inside material, never strengthen. The Beer-Lambert Law states that X-ray intensity decays exponentially when it's traveling inside homogeneous material. Here mu is a positive number. It's specific to a material and indicates how strongly the X-rays are attenuated when traveling inside that material. The number S is the length of the path that the ray travels inside the block. The mathematically desired line integral is the product mu times S. How can we determine that from the things we can measure? Divide both sides of the Beer-Lambert equation by the positive number I0. Take logarithm. Use the calculation rules of logarithm. Move the terms to opposite sides in the equation. The left-hand side is now the line integral. And the right-hand side contains only things we can measure. Wait, what? How can we measure I0? By sending an X-ray through empty space. Let's study the case of an X-ray traveling through two homogeneous blocks. The line integral of two blocks should be twice as much as the line integral of just one block. Take an initial intensity of 1000 X-ray photons. They all reach the detector. Applying logarithm to the photon count gives 6.9. Now choose a ray that goes through one block. I have chosen the half thickness of the material so that exactly half of the incoming photons will make it through. We again take logarithm. The ray that goes through two blocks has lost half of its photons in the middle. Going through the second block reduces 500 photons to only 250. Now we have the logarithms of all the three rays. Subtracting the logarithms should now give the line integral. Indeed, the empty space ray has a zero integral. That's correct, as there was no stuff in the way of the X-ray. Furthermore, the two-block integral is twice as large as the one-block integral. Now we have transformed the intensity data into line integrals. Physical material is kind of sunglasses for X-rays. Two blocks is like double shades compared to one block. Now is the time to step from homogeneous blocks of material into something real, such as a human head. X-ray intensity again decays exponentially, but the parameter mu is changing depending on the tissue where the ray travels. Bone attenuates radiation strongly and has a large mu. Soft tissue, such as the brain, is easier for X-rays to travel and has a smaller mu. The Beer-Lambert law needs to be formulated in a way where mu depends on the location x. Repeating a similar calculation than before, we arrive at an equation connecting the line integral to numbers we can measure. Now you know how to get from X-ray detector pixel values into the line integrals used in the radon transform. However, the full story is not quite that simple. In this video, we assumed an ideal detector, perfectly counting the number of photons without any errors at all. This is too good to be true in the real world. In the next video, we will concentrate on measurement noise and other imperfections that are inevitable in practice. Stay tuned.